Teaching rules and procedures in fractions is something that happens every day in classrooms. If it happens after there's conceptual understanding and students see the meaning of the math, I think that's fine. But even when we're doing this, we need to be explaining to students and having them be explaining back to us why they are doing the things that they're doing whenever they possibly can. Complete the following problems after you pause the video and see if you can include language out loud while you are completing them that explains why you're doing what you're doing as you follow traditional rules and procedures for adding fractions. As we teach procedures, we need to remind students about the realities of what a fraction is. For example, the bottom number of a fraction, the denominator, only tells us the size of the piece, the name of the piece. It's just like saying an apple is an apple and an orange is an orange. A fourth is a fourth, a sixth is a sixth. So if our denominators are the same, then we're adding like things. And then we can just add them together like we do anything else. If students understand that, adding with like denominators is very easy. Here I have 2/4. Here I have another fourth. They're all fourths. They're the same thing. 2 plus 1 is 3. And fourth is just the name. In this problem, I have 5/6 and I'm adding 1/6. 5 plus 1 is 6, just like 5 plus 1 of anything is 6. And the sixths, the denominator, is just the name. I also know that if I have 6/6, that means I have all of my pieces, which is the same as one whole. When we move to denominators that aren't the same, we need to make sure we're reminding them why the denominators need to be the same. So we can't add things that are different. They have to be alike. Apples can be added to apples. Oranges can be added to oranges. Fourths can be added to fourths. Eighths can be added to eighths. But we can't add fourths and eighths because that's like adding apples and oranges. They're not the same. We have to change one to match the other. And when we do that in fractions, what we're doing is we're cutting the pieces smaller so the pieces are all the same size. So could we change a piece that's a fourth to be an eighth? Yes, we can. If we cut it in half, then we'll have an eighth. So what we're going to do is take it times 2 to get 8. But we know it's a mathematical law that if we do something to one part of a fraction, we have to also do it to the other. So if we take 3/4 times 2/2, now we have 6/8. 3/4 and 6/8 are equivalent fractions. Now we have eighths, so we can add another eighth. 6/8 plus 1/8 is 7/8. On this problem, we can't change a 5 to a 2 very easily by cutting it into pieces, and we can't change a 2 to a 5 very easily. It just doesn't work very well. So we're going to have to make our pieces smaller. We're going to have to take both of those and cut them into smaller pieces that are the same size. We can do that by taking this fraction times 2/2 and this one times 5/5, and then we'll end up with a denominator of 10 for both. When we take a fraction times 2/2, 2/2 is the same as 1. If we take something times 1, it doesn't change what we have. 5/5 is the same as 1. So if we take 1/2 times 1, we're not changing what we have. So what we're doing here is we're cutting these pieces smaller so that we have tenths. We're cutting each of the fifths in half to give us tenths, and we're cutting each of the halves in 5 pieces to give us tenths. So what we have then is 4/10 plus 5/10 equals 9/10. This fraction is the same as this, equivalent fractions. This is the same as this. They're just cut into smaller pieces. And because we have the same denominator, the same bottom number, we can add them together, like apples and apples. Complete these problems using traditional methods and see if you can use the language that explains the meaning of the math. Pause the video, and then when you're finished, see if your thinking aligns with mine. In this first problem, our bottom numbers are already the same. Our denominators are the same, which means our pieces are the same size. So we can just subtract how many we have. If we have 2 of something and we take away 1, we have 1 left. 2/3 minus 1/3 is 1/3. In this one, we have eighths and we have a half. Those pieces are not the same size. But if we cut our half into smaller pieces, we can make it eighths. So if we take our half times 4/4, cutting it into smaller pieces, then we will have 4/8. Then our bottom numbers match, our denominators match, which means our pieces are the same size. 7/8 take away 4/8 is 3/8. This one's going to be a little more difficult because we can't cut pieces into the same size if we have 3 here and 4 here. We're going to have to cut both of those into smaller pieces to make them match. So this one we will take times 4/4 to get 12ths. This one will take times 3/3 to get 12ths. That means our new problem will be 8/12 take away 3/12 is 5/12. So what we've done is we've cut each of the thirds into 4 pieces to get 12 total pieces. We've cut each of the fourths into 3 pieces to get 12 pieces. And we've made sure that we take the top number times the same amount, because that's just like taking it times 1. 2/3 times 4/4 is like taking 2/3 times 1. 1/4 times 3/3 is like taking 1/4 times 1. So we're just cutting the pieces into smaller pieces that match, and once those pieces match, then we can subtract, because we can subtract like things. Complete these 2 problems using the procedures you were taught, the rules you were taught for multiplying fractions. And then, after you've paused the video and done that, see if your explanations align with mine. When we learn the rules for multiplication in math, we learn top times top and bottom times bottom. 2 times 1 is 2, 3 times 2 is 6. In this problem, 5 times 1 is 5, 6 times 3 is 18. Why does that work? We're taking 2/3 times 1/2. So we're taking 2/3 1/2 times. That means that we're cutting each piece in half. So instead of having 3 pieces, we now have 6 pieces. That's why the multiplication process works. In this particular problem, we have 5/6, and we're taking it times 1/3. We want 1/3 of the 5/6. That means we're cutting each one of those sixths into 3 parts to get 18 parts, and then we're looking at the top numbers to see how many of those parts we have. So in multiplication, when we take the bottom number times the bottom number, it tells us how we're cutting our pieces. We're cutting them into smaller pieces so that the answer will make sense. The top number times the top number tells us how many of those pieces we are using. This is exactly like when we drew pictures of multiplication of fractions, except when we were drawing pictures, we actually drew the picture first, and then we cut the pieces at the very end, if we needed to make sure the pieces were the same size. When we use the rule, the procedure, we're actually cutting the pieces first, and then doing the operation to find out how many pieces we have. Just to make that clear, if I have 2/3, like I have here, when I multiply, I'm saying I need to take them times 1/2. That means I need to cut each piece in half. So I'm actually doing that first. I'm cutting the pieces in half so that I now have 6 pieces. Then I'm seeing how many of those pieces that I will actually be using. I started out with 2/3, and if I take half of my 2/3, if I cut them in half like I did right here, I have 2 pieces. But it's not 2/3 anymore, it's 2/6 because I've cut each piece in half. And I did that cutting by multiplying the bottom number times the bottom number. The rules for dividing fractions are very strange. If you think about it, there are mathematical ways that we can teach the meaning of these rules, but to be honest, for elementary students, it's very confusing. Complete these 2 problems the way you were taught using traditional methods, and see if you can think about what it is you're actually doing as you follow those rules. Pause the video, and once you have them finished, see if your thinking matches mine. So traditionally, what we would do is we would say, I have 3/4, and I'm going to divide it by 1/4. Instead of dividing, I'm going to multiply, and I'm going to multiply times the reciprocal. Once I have that set up, I might be able to cross divide to make my multiplication easier. Then I take top times top and bottom times bottom, just like I did when I multiplied. So for this problem, I have 2/3 to start, Instead of dividing, I'm going to multiply. I'm going to multiply times the reciprocal. I'm going to see if I can cross-divide to make it easier, which I can't. My answer is 4/3, top times top, bottom times bottom, and that 4/3 is the same as 1 1/3. So what have we really done here? This is very confusing. What I teach my students is we're doing two inverse operations. I need to convince them that this is true before we can even start. What I tell them is they already know how to multiply fractions, so we don't really need to learn how to divide. We don't really need to learn something new. We can use multiplication, which we already understand, if we just make a couple of changes. So then what I have to convince them of is two negatives make a positive. Now hopefully they know this from other mathematical work, but if they don't, I can convince them using other methods. For example, I can say to my students, Susie, if you're having a party tonight and Jane says she's coming, will you see her there? And Susie says yes. And then I say, what if Jane tells you she's not coming? Will you see her there? And Susie says no. And then I say, what if Jane tells you she's not coming? Will you see her there? And usually students have to think for a while. If she's not coming, that means she is coming, which means the answer is yes. So these two negatives make a positive. I can convince them of this in other ways. I can have them stand facing a certain direction and say, I want you to reverse, and then I want you to reverse again. And they can understand that two reversals means I'm back where I started. So when I divide fractions, where are my two opposite operations? Where are my two inverse operations that would act just like saying, I'm not going to the party? Well, instead of dividing, I multiply. There's 1. I do not divide. Instead, I multiply. So dividing becomes multiplication. There's one reverse operation. Instead of dividing by the number that's given, I'm going to divide by the reciprocal, which is exactly the opposite. Those two are complete opposites, which means there's another inverse operation. So here's my first one, here's my second one. Two inverse operations means I can do exactly the same thing by switching those two things. And I already know how to multiply fractions, so if I do those two reversals, I don't have to learn something new. In some ways, that's not very mathematical. And it's kind of hard to teach this to kids, why this works. It's a little tricky, to tell you the truth. But I think in some ways it can help them make sense. The best thing, of course, is for them to think conceptually. How many 1/4 are there in 3/4? They shouldn't even have to work this out. It's common sense. If I have a piece that's 1/4, how many of those does it take to make 3/4? And the answer is 3. They should be able to work that out in mental math without even doing the calculation. Here, this is a little harder for them to see. How many 1/2 are there in 2/3? However, they should be able to picture that 2/3 is more than a half. So if I have 2/3, there's my 2/3 that I started with, and here's my half. How many of those halves can I fit in those 2/3? There's one, and there's another third. That's a little tricky for them, but at least they can use it to estimate and envision what's happening. We looked at these problems before. Complete these problems with the rules and procedures you were taught, and then see if your thinking aligns with mine. In some classrooms, there are teachers who insist that students do this kind of work by changing the mixed numbers to improper fractions. And certainly students should know that a mixed number can be an improper fraction and the other way around. But we want students to think logically. So in this first problem, we want them to be thinking 4 plus 2 is 6, 2/3 plus 1/3 is 3/3, 6 3/3 is the same as 7 because 3/3 makes a whole. 6 1/4 take away 3 3/4. I can't take 3/4 away from 1/4, so I need to take my whole, break it into fourths, because that's the name of the piece that I'm working with. That would be 4/4, And I already have 1 here, so if I add that together, I would have 5/4. 5/4 take away 3/4 is 2/4. 5 take away 3 is 2, and my answer is 2 and 2/4. Here, we want students to be thinking, I have nothing, take away 1/2. Since I have nothing here, I need to get some halves. How can I get them? I can take a whole from the 8, which means I now have 7. I can break that whole into 2 halves, because 2 halves is a whole. I can say 2 halves take away 1/2 is 1/2. 7 take away 3 is 4. Again, we want students to be able to do this with mental math whenever possible. In this problem, they should be able to do this mentally. They should be able to picture it. In this problem, they should be able to say, well, if I take a half away from something, I'll have a half left. I don't have 8 anymore, I have 7. And they should be able to almost come up with these answers mentally by just picturing it. What we don't want them to have to do is something where they go, 2 1/3 is the same as 3 times 2 is 6 plus 1 is 7. 7/3. 4 2/3 is the same as 3 times 4 is 12 plus 2 is 14/3. 7/3 plus 14/3 is 21/3. 21/3 can be simplified to 7. That is so complicated, and we're having students go through all those steps for no reason. So if we're going to have students convert from improper fractions to mixed numbers and back, we should make sure it's because that's really the only way for them to do the problem, to see the meaning of the math. So the big idea here is, even when we're teaching procedures with fractions, adding, subtracting, multiplying, dividing, we want students to be able to explain why they're doing what they're doing. Why does it work? That why, having them say because, is so important. It shows us that they're not just memorizing rules and following them, something that could cause them to get all the rules mixed up at some point. It means they understand what's happening with the math.